Hey everybody, it's Ripley back again. So today we're going to talk about what derivatives do to the shapes of graphs, but way more importantly, we're going to talk about how to use derivatives so that we can sketch curves without having to pick up our graphing calculators, because sometimes it's just faster, particularly when we start talking about optimization or things of that nature. Okay, so which is a topic for down the road. I'm sorry about that. I just sort of threw that at you. All right, so what I'm going to do is I'm going to give us a function to think about, all right? And the function that we're going to, excuse me, the function that we're going to use to just have ourselves a conversation, it's going to be simple, it's going to be easy to use. I'm going to use f of x is equal to, and again, I'm just trying to keep this simple, 2x cubed plus 3x squared minus 36x, okay? It's just an interesting function. Okay, now we've already talked about what first derivatives give us, but let's go through it. By the end of this lesson, you're going to be able to use first and second derivatives to sketch functions without using your calculator, without using your graphing calculator, and then of course we're going to use graphing calculators to determine whether or not we got it right. Okay, so the first thing I'm going to do is I'm going to take a derivative, and there's a saying in differential, well, in all calculus, when in doubt, take a derivative, right? Just take a derivative and see what happens. All right, so if I take the derivative of this, I get 6x squared plus 6x minus 36, which this thing is just begging to have a 6 factored out of it. So I got to get x squared plus x minus 6. Now, what do we do with derivatives always? What's the first thing that we always do? What's the most interesting part of graphs? Well, I would argue that it's when they level off. And when graphs level off, we know that their derivative is equal to 0. Okay, so I'm just going to set this thing equal to 0. Now, why am I doing that? Because I'm going to solve for critical values, and then I'm going to use a Ripley doodle diagram to play with this. Okay, and then we'll sort of summarize what we did. So this is equal to 6 times x plus 3, just a quick factored trinomial here, x minus 2, which equals 0, right? So I'm going to have critical values at x equals negative 3 and 2. So I take my Ripley doodle diagram, I throw f primed on my Ripley doodle diagram. The most important thing about using a Ripley doodle diagram, no doubt about it, is labeling it. Otherwise, you're going to get really, really confused. I'm going to slap negative 3 on here. I'm going to slap 2 on here. Now, again, the reason that I label this guy is so I know which of these two functions to use. What I will often get with kids is they'll say, oh, okay, cool, negative 3, and I'm going to plug it in here. Right? Well, don't do that. Or they'll say, let's pick a value between negative 3 and 2, like 0. Remember, on a Ripley doodle diagram, you only want to put your critical values, never anything else. Otherwise, it can be confusing. Excuse me. So let's pick 0. Now, a student may throw 0 into f of x, and then you'll end up with 0, 0, and you're like, oh, wait, what? Why is that 0, 0? That should be oh, okay. Now, stop. We are using our first derivative to get information about the function. I'm going to plug 0 into this guy. If I plug 0 into this guy, it should be relatively obvious that I end up with positive, positive, negative, which is a negative. Okay? If I plug negative 5 in, I will get positive, negative, negative, which is a positive if I multiply all those out. If I put 15,000 in, or better yet, 3, then I get positive, 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 which is a positive. Now, remember, let's do a little side note over here. If f primed of x is greater than 0 on some interval, let's just say from a to b, and I'll make it open, this implies f increases on ab. We got this little running total over here of information. If f primed of x is less than 0 on ab, this implies f decreases on AB. Easy. So what I have is, I have a function that increases, levels off, decreases, levels off, and increases again, which gives me this wonderful piece of information. I know that my function is going to have what appears to be a rel max there, and a rel min here. That's pretty easy. Now, this is not an extreme value theorem setting. This is not a closed interval. Remember, the extreme value theorem only works when we're in a closed interval. So I know that this function increases throughout. Okay? Now, what do you think the second derivative, so I'm going to put a little, you know what, let's do this. I'm going to put, this is going to be my little sidebar. What do you think that the second derivative tells me? Well, I can take as many derivatives as I want, right? But let's figure out, what does f double prime give us? Well, think about this. Let's see. The second derivative is to the first derivative as the first derivative is to the function itself, right? That makes sense, because the second derivative is just the first derivative of the first derivative. So if f double primed of x is greater than 0, doesn't that imply that f primed of x, which is equal to the slope of the line's tangent, oh, that's increasing. So wait a second. Okay, let's ponder this for a moment. If the second derivative is greater than 0, then the first derivative is increasing. If the first derivative is increasing, then the slopes of lines tangent are increasing. So let's think about two ways that that can happen. Let's see. Let's make that be a slope of a line tangent, and that's going to increase. Another slope of a line tangent, another slope of a line tangent. So if I sort of connect the dots here, then I'm going to have a function that looks like this, aren't I? Right? Now, look at that function. In mathematical terms, we talk about this curvature of the function as being concavity. So this right here is concavity. And in this case, this is concave up. It's concave up because the concavity appears, if you think of the concavity as being a bowl, then it appears that the bowl shape is pointing upward, not perfectly straight up, but upward. It's got this, I should make that, let's use a different color and draw over the top. I'm going to exaggerate this a little bit. It looks like that. Now, that is not the only way that the first derivative can be increasing on a curve. All right, let's look at another way. The curve can actually be decreasing and have the slope of the line's tangent be increasing. Watch. So let's say that my curve looks like that. Now, you're like, wait a second, Ripley, all of those slopes of lines tangent are negative. And you'd be right, but look, let's say that oh, that's awful, is -3, and that is -1, and that is -1/2, and that is -1/4, and that is -1/10. Well, if I go from -1 or -2 or -3, whatever I said, to -1/10, I am increasing. I am moving from left to right on the real number line. Hey, and guess what? Look at my concavity again. It's concave up. So what that tells me is if f double primed of x is greater than 0 on an open interval from a to b, this implies that f of x is concave up on AB. Two ways. I could be increasing in concave up or decreasing in concave up. Now, what about if f double primed of x is less than 0? What do you think that implies? Well, let's look at it graphically, and then I'm going to add some more information on the next page. Well, what would be happening? This would imply that f primed, which is equal to the slopes of lines tangent, is decreasing. So if I'm increasing, if my function f, I got to make sure that we understand that this is f and that this is f. I think I said that a bunch. But if my function is increasing, but my slopes of lines tangent are decreasing, wouldn't that look something like that? Because now my slopes of lines tangent are going wachang, wachang, wachang. Look at the slopes, they're decreasing. Likewise, if my function itself is, it's hard when you're writing down around your belly button. If my function itself is decreasing, right, and my slopes of lines tangent are decreasing, I'm going to get that, right? -1/10, -1, -3. And in both cases, look at the concavity. The bowl shape is pointed downward, which means that I am concave down. All right, so let's do some summarization on the next page, and then I'll pop back over here because I want to play with this function some more. All All right, let's do some summarization. So we know this. I'm going to keep it simple. F primed of x less than 0 implies f is decreasing. F primed of x greater than 0 implies f is increasing. F double primed of x less than 0 implies f is concave down, which you'll hear is CCD. And f double primed of x greater than 0 implies that f is concave up. CCU. Nothing to it. Now, let's apply that, because we have already done increasing, decreasing stuff with Ripley-Doodle diagrams, but let's apply our new found information about second derivatives to this function. Now, if you notice, you can be really, really systematic about this. So, for example, look, I can say right now, based on the work that I've done with the first derivative, I know that f, I'm going to be a little bit lazy, I know that f is increasing on the interval from negative infinity to negative 3, union 2 to infinity. Notice that I use open brackets at negative 3 and 2. Why? Well, because the first derivative equals 0 at negative 3 and 2. And if your derivative equals 0, you are neither increasing nor decreasing. All right? It's decreasing, let's see, between negative 3 and 2. It has a rel max at negative 3. Now, I'm going to be lazy here, and I'm just going to go f of negative 3, whatever that number is. It's got a rel min at 2, comma, f of 2. I mean, I could plug it in and deal with it, but let's not do that yet. All right, now, let's deal with the second derivative. I know that f double primed of x is going to equal 12x plus 6. And if I set that equal to 0, it should be relatively obvious that I get a critical value at x equals negative 1/2, right? Just solve for x. That's easy. Let me make sure I did that right. I did. All right, now, again, label your Ripley-Doodle diagram. Always. Again, only put critical values on your Ripley-Doodle diagram. And then let's test values. Let's see, notice it's labeled as f prime, so I know where to test my values. That keeps me out of trouble, because now I've got two other functions floating around. This can get really confusing. So let's put negative 1 in. Should be relatively obvious when I put negative 1 in, I get a negative. Let's put 0 in, I get a positive. Now, that already gives me information. I am all set. I know that f is CCU on negative infinity, or excuse me, try that again, on negative 1/2 to infinity, and CCD on negative infinity to negative 1/2. Again, notice that I leave open brackets at negative 1/2 because the second derivative equals 0 when x equals negative 1/2. And if your second derivative equals 0, you have no concavity. That's what that implies. Now, let's get a little crazy here. Let's look at this, because I got my little stick figure over here. Now I'm going to be the Bob Ross of differential calculus. I'm going to make a pretty little function. So I know that I change concavity at negative 1/2. So I'm just going to guess, and I'm going to put negative 1/2 like right about there, right? I mean, these are really horribly drawn, horribly scaled. I guess they're not too terrible because I've only got two values on it, but I'm just guessing negative 1/2 is about there. Right? And it says that it's concave up from negative 1/2 to infinity. So remember, this is a stick figure of f. So what I'm going to do, let's put negative 1/2 about there. Let's actually kind of split the difference, right? But it doesn't matter. All right, anyway, sorry, I just went off on myself there for a second. It's concave up. So let's add a little detail. Pretty little function. That's my Bob Ross, by the way. I need to erase. See, Bob Ross poor Bob, didn't have, Ross that is, a Wacom bamboo tablet like I do. All right, concave up from negative 1/2 to infinity. Concave down, hey, look at that. That's kind of pretty, right? And it appears, notice that f is a cubic, and this looks pretty darn cubic, right? I have all this information. I know when it increases, when it decreases, when it's concave up, when it's concave down, clearly what its rel max is, clearly what its rho min is, right? Now, all I have to do, I gotta figure something out though here, because there's this little point right here where it appears to change concavity, and that's at -1/2. Well, let's add that to our definitions. Excuse me. We have a definition, of something called an inflection point, and this inflection points can be very, very confusing. All right, let's go back to that. All right, a point is called an inflection point, which I will refer to as IP, and you'll see that's how I'll note it in the problems now and in the future. An inflection point, if, let's see, what the heck am I doing? Sorry, if the point lies on the function, if the point lies on a continuous function, continuous function. It's funny, I'm making these videos during class time and I had a kid just trying to come in. I'm like, no, don't come in. All right, if the point lies on a continuous function and the function changes concavity at the point. In other words, an inflection point is a point where concavity changes. However, that function has to be continuous. Now, by change of concavity, I mean it goes from concave up to concave down, or concave down to concave up. All right, that's what happens. It's got to change concavity. You can have weird functions where you've got a function, let's say, that is concave down, and then it levels off, or it doesn't level off, but it loses concavity for a minute. Now notice this is still a continuous function, right? So I'm concave down, then I lose right here, f double primed would equal 0 for all these values because straight lines, all lines are straight, but lines don't have concavity to them. And then all of a sudden, I'm concave up. Notice my concavity goes this way. In this case, there are no inflection points. There are no inflection points because I went from concave down, second derivative less than 0, to concave up, right? Second derivative greater than 0. However, there wasn't a single point at which that happened. Okay? All right, so if I stumble back to my good friend, this guy, I know that f has an IP at -1/2, comma, f of -1/2. And I'm done. That's it. This is all of the information. I can sketch this graph. Now, this is a pretty, let's see, I know that, what do I know? I know f of 0 equals 0. So let's put -1/2. I'm going to put, just for giggles, I'm going to put this set of coordinate axes on here. Now, the reason I'm doing this is I'm actually going to graph this function on my calculator. I got to add pretty little curves. Pretty little curves. Just like this, and I'm going to see how close we got. Okay? So over here, oh crud, I forgot what it was. 2x cubed plus 3x squared minus 36x. So let's go. Oh, I'm here already, aren't I? 2x cubed. Was it plus or minus? What the heck? Plus 3x squared minus 36x. So plus 3x. Whoops. Oh, I hate it when I do that. Delete. Oh man, that drives me nuts. And is it gone? Let's try it. Oh, delete. And then over. Plus 3x squared. Silly Ripley. 3x squared. And then plus 36. Was it plus or minus 36x? Getting old. Minus 36x. I'm glad I checked on that. Minus 36x. And let's just go zoom standard, which is zoom 6 on this bad boy, and let's sketch it. Let's see how we did. Wow. Well, clearly my scale, let's set my window. Let's go to my y min. It appears I got to get down there a little bit. Let's go y min equals, I don't know, -50. get crazy with it. And then y max equals positive 50. And then let's graph that. Boom. Oh, wow. Wow. So I got to get my y max up there just a little bit more. So y max will go to 100. I'm going to mess with my y scale too. So I'm going to go 100. And then I'm going to make my y scale, let's do 10 instead. Because otherwise you get that really thick bar that you probably noticed. Let's see. Yeah! That kind of looks like what I did once I tweaked my scale a little bit. And I can figure out what these maxes are too, right? Just by going second calc. You should have probably already known this from your Algebra 2 and your pre-calc. I'm going to go max. I'm going to scooch over here. This is a good little review just in case though. If I want to figure out what the max value of this thing is, come on, baby, get over there. I can scooch this way. Let's see, that's cool. I'm on the left-hand side, hit enter. Go over, I don't know what that word was I just said. Go over this side, hit enter, and then no guess, waste of time, what kind of? And I end up with -3, 81. Now, why does it do this -2.9999? Well, that's because it's doing it numerically, and it only has to get within tolerances that it has established for itself. Now, that max is at -3, 81. Let's go back and look at our work. Hey, -3, f of -3, and had I been a little less lazy, I could have figured out that f of -3 is 81. Likewise, I know that my relative min, ooh, I wonder if it's going to let me do it. Let's go second calc. And I want to do a min, which is 3. And I'm going to cruise over yonder. All right, try not to bore you guys too much. Come on. Right over there. Whoa, where is it? Oh, didn't like that. I can't do that. Come on. Go. Go. Oh, okay, that looks pretty good. It's going to, oh, it went the other way. Dang it. All right, try this. Go around the horn. Sorry, you guys. Boom, hit enter. Go to the right. For those of you that haven't done this before, it's a lot smoother on your own calculator. This thing's lagging because it's fighting with the OS on my desktop. Okay, I don't want to guess. Hit enter, and look at that, 2.02000023 because it's within the tolerances, and that looks to be -44. And that, I mean, if I look back here, that's kind of what we're looking at. Now, mine was flatter because I was sort of pinched in, but look at that. Like, I was higher over here and lower over here. I mean, this thing is higher above the x-axis than this thing is below the x-axis, and I nailed that, right? That's not too bad, kind of. All right, anyway, so that is how we use first and second derivatives to sketch curves. Now, I want to give you one last piece of information before we send you on your way. And I'm going to give you one more example about how to deal with things like asymptotes and places where functions don't exist. All right, and that doesn't take very long at all. I want to give you what's called the second derivative test. The second derivative test. Now, we can use the first derivative test. And what the first derivative test is it's basically using the Ripley-Doodle diagram and saying, okay, I'm going to use my first derivative. I know that if the derivative of my function goes from positive to negative, I have to have a max. Whether it's relative or absolute, we have to figure out. I know that if my first derivative goes from negative to positive, then I have to have a min, whether it's relative or absolute, global, whatever you want to call it. That remains to be determined by the person working on the problem. So that's the first derivative test. If derivatives go from positive to negative, max. If derivatives go from negative to positive, then I have a min. But there's a second derivative as well, and it's actually pretty cool. The second derivative tells me this. If f double primed of x is less than 0 and f primed of x equals 0. Now, I'm going to put this over here because I don't want to chew through all my space. Let's think about what that looks like. If in this case, let me give it some blue. What would that look like? Well, I would have a function that was concave, what? Down, right? Because second derivative is less than 0. But it also at a point, I want to do, instead of x over here, I want to put c's because this is at a very specific point and I don't want you to assume that it's for all points. So let's put c's in there. If f, there we go. If f double primed at c is less than 0 and f primed of c equals 0, then what does that look like? Well, let's put c here. Well, I know that the function is concave down, but it also levels off at c. So it's going to go, oh, it's going to be concave down and it's going to level off. Oh, let's move my, man, that is just horrific. Again, when I get to the bottom, I'm writing right around my belly button, which is hard to write. What do I have? Guess what? It's concave down and it levels off. This implies f prime of c is a max. Likewise, if f double prime of c is greater than 0 and f prime of c equals 0, what does that have to imply? Well, let's go over here again. Let's try and do this a little better this time. Here's c. I've got at c, my function is concave up, but I level off as well. Concave up, leveling off. Guess what? This implies that f prime of c is a min. That's your second derivative test. Super helpful, and you can do it really, really fast, particularly if you have a good function. So, like I said over here, now this is going to seem a little silly. Whoops, this is going to seem a little silly because I've already taken all the derivatives. But look, do you agree that when x equaled -3, the first derivative equaled 0? Yes, and the second derivative was negative, which means I leveled off and I was concave down. When when x equaled 2, the first derivative was also 0, and the second derivative was positive. Guess what? I leveled off and was concave up. And I can take those derivatives really fast and not have to go through this whole process if all that I want is maxes and mins. All right, second derivative tests can be super duper helpful. All right, let's do one last one because I want to talk about what happens if I've got, I'm going to keep it so simple. This video is getting long too, so I want to wrap it up. What if I've got 1 over x? Oh, we know what 1 over x looks like. And I want to see if this thing manifests itself. If this thing manifests itself through all those derivatives. This is y equals f of x. In other words, the rules that we used for a continuous function for this polynomial back here had better be consistent, and we better be able to use them for, oh, wait. They better be consistent for all functions, right? All right, well, here we go. I want f prime of x. That's -1 over x squared. Set that equal to 0. My critical value is at x equals 0. Now notice what we have is, now let's ignore the fact that we know what this function looks like. I know that I'm getting a critical value at x equals 0, not because the f prime of 0 equals 0, but because f prime of 0 does not exist. Remember, critical values are defined as values of x for which the first derivative either equals 0 or does not exist. So when I go to do my Ripley-Doodle diagram, I'm going to put x equals 0 on here, but I'm going to combine that with the fact that we know that we have a vertical asymptote on f of x equals 1 over x. So I'm actually going to put a vertical asymptote on my Ripley-Doodle diagram so I don't confuse it with a max or a min, because that can get really confusing. Watch, here's why. Don't forget to label. When I plug in -1 and I stick it where? Into my first derivative, I know that -1 squared is +1, so -1 is always going to be negative. When I plug in +1, I'm going to get another negative. Now this is where it gets kind of confusing, because if I try to draw a stick figure, I end up with a stick figure that looks like that. You're like, wait, what? Well, let's add a little more dimension to it. If I take the second derivative of x, well, remember, this is x to the -2, so this would give me a +2 over x cubed. Again, if I set this equal to 0, I always want to set any derivative equal to 0. Hopefully I made that clear. Always set any derivative that you take equal to 0, because then you get critical values. I get a critical value again at x equals 0. All right, so I put f double primed over here. Again, I know that at x equals 0, I'm getting vertically asymptotic behavior. Plug in -1, I end up with a negative. You should be able to see why. Plug in +1, I end up with a positive. Now here's where it can get really misleading. I know that this guy is concave down, and I know that this guy is concave up. All right, I know that concavity changes. So you may say, oh, Ripley, notice the color of the pen I'm about to use. Inflection point at x equals 0. Nope, no, frowny face. Why? Because the function is not continuous at x equals 0. All right, it doesn't exist. In other words, it has to be a point that lives on the curve at a place where the function is continuous. Otherwise, no dice. Now you may say, well, Ripley, what if I put a point right there? What if I turn this thing into a piecewise function, right? And I let this thing be 0 when x equals 0, and I let this be 1 over x when x is not equal to 0. Well, we run into that same problem. We're not continuous. That's sort of disingenuous, isn't it? You're like, well, I'll just make an inflection point. Yeah, but you still have lost continuity. All right, now, the moral of the story of this is let's make sure that that our Ripley-Doodle diagrams and our derivatives still work. Well, clearly, f of x equals 1 over x always decreases. Whoop, whoop. Let's see, it was concave down to the left of 0. Yep, concave down. It's concave up to the right of 0. Yep, concave up. So look, it still works. The problem is because of this weirdness around the asymptotic behavior, we have to remember how all of our algebra 2 stuff about how functions behave. So we can, again, I'm going to say this over and over and over again, you can't just discount and discard all of your old information about the behavior of functions. That's why it's so important to think visually. When you're doing graphical analysis, you have to think visually. What does the function look like? What do I know? Without having to pick up the idiot box. Remember, this here calculus is only as smart as the idiot pushing the buttons. That's why I call it the idiot or the monkey box. It's only as smart as the monkey pushing the buttons. And we have all made silly monkey errors dealing with our TIs, all right? Or our Casios or whatever we're using, all right? So remember, a calculator is a tool. The second you turn it into a crutch, the job of your teacher is to kick that crutch out from under you. So don't become too reliant on your calculators. I tell my students in my class that try not to touch your calculator unless you absolutely have to until the very end to check your work. Okay? It'll make you a better mathematician, it'll make you a better grapher, and you'll be using your calculator in an appropriate way, and that's to check your work. All right, enough of me yapping at you. This is a long section. Thank you for bearing with me, and I'll see you in the next lesson. This should be a fun one.